little bit to try to tell you how these two worlds, I mean, it's really difficult to represent it or so. First I thought I'd say it's the rational and the irrational numbers together, they make the real numbers or so. But that's kind of not good, because the irrational numbers are not a field. Whereas I can say here, the discrete measures, they're a closed subspace, and the absolutely continuous are a closed subspace. But somehow, and now changing the perspective, from the distance or in the weak star topology, you can approximate one from the other. So somehow you have, you cannot say this is L1 a picture and then I have where should I put the discrete measures? If you give me any function in L1, I say, okay, you're giving me the probability distribution with continuous distribution. I know how to approximate distributions, I mean probability distributions by discrete measures. So there must be some nearby discrete measure. If you tell me I have a linear combination of 5 Diracs, it's clear what you do. You put Gauss functions small enough at those positions with amplitudes. I mean, you do ST rho of G0 large rho, so it's very needle-like. The amplitude chosen as the discrete measure tells you. So every discrete measure can be approximated in the weak star sense by this. And that's why I thought that maybe this is a good possible picture. I mean, let's say the green ones, I don't know, are the L1 guys, and the blue ones are the discrete measures. They all sit in the red box of all bounded measures. And again, this gives you the wrong impression that every measure is either green or blue. So somehow maybe I should leave, but I cannot say it's everywhere dense. I mean, if you give me anything, I can approximate it in both colors. But on the other hand, most of the random objects are mixtures. I mean, you can have a continuous density on this side, and then some Diracs here, or you add a L1 function with it. So in that sense, I'm also having some discussion with a colleague or so who tries to say, well, we have smooth function and rough functions. Yes, in practical life, most of the time people, engineers would say, we have now a discrete signal and then we use discrete theory, or we have a continuous signal. But then you have a jump combined with a Dirac. I mean, yes, constant 1 plus delta is Fourier invariant. Great, because they switch positions. It's nice, but you cannot say it's rough, because it's constant 1 is most of the place it's very smooth. Constant is the best smoothness. You cannot say it's discrete just because there's a Dirac, just that one Dirac. I mean, on the other hand, it's here. I mean, so in that sense, we should think, sometimes I'm saying it's like minerals. You're going in some nice exhibition and they show you these nice minerals. But look at the mountains. I mean, 99.999% is just stupid stones, I mean, which are not interesting. So we're focusing, the attention is focusing on the interesting objects, of course, and it's very meaningful to work with LP spaces and so, but yeah, I don't know. I think I will wait for Professor. Yeah.
Like when you work on the complex valued function, you mentioned about like continuity, say continuous function having compact support.
Yeah.
And plus it is complex valued.
Yeah.
Then one must be careful on basically.
Yeah. So kind of the statement was meant to be, if you take the signum, the analog of the signum, which is the quotient between the function value and the absolute value, which is simply the phase. So kind of if I have a graph in this, usually I'm saying this is my time axis, and the graph is smooth and continuous if my hand is moving smooth. And now you can even explain winding number. If I turn around 3 times, this is a complex valued function with winding number 3. If I do this, I mean, with one hand and leaving this, I cannot get anything more than winding number 1, maybe. Let's say normally you would say, okay, it's going like this, coming back, but then it comes back. So if you pull, you can make a straight line, that's winding number 0. But if the phase is like this, it's rotating more and more, but it's also going to 0. It's very discontinuous in phase, but still nicely going to 0. So one should not say, because the function is going to 0 and having compact support, the phase function must be nice. It's absolute value 1 and is rotating like wild because you divide through when you come near the end. Okay. I think no. Yeah, no. I was answering one question, and we just have to say that I'm ready now. Sir?
Okay, ask.
Yeah. Okay. So I'm glad that we can continue today going towards the main goal of this course, which is going in the direction of distribution theory. So I will show you my own simplified distribution theory. So essentially, when I talk to engineers, my claim would be you should learn distribution theory, but you don't have to do it in the traditional complicated way. There is a simplified version, and I will see if you agree at the end of the course that it's an easier way to understand these things. Before doing this, let me just repeat a few things and show you one little picture that I was making up last night for the course. Because what we have now, I've just tried to summarize it in the discussion. We have the space of continuous functions with compact support, and close it up to get the Banach algebra C0. It will be explained. This I will try to explain it. Yeah.
Suddenly I'm
No.
seeing on D.
No. Yeah.
MB
No.
or D?
Yeah. No. I try to explain. The point will be my point will be to explain. Yeah. No. You're not supposed to understand it from the picture, but I want to make it. No problem. So we have C0. Then we have the bounded measures, which has now two roles. One is it's the dual space. For every Banach space, we like to look at the dual space. But it's also the description of the operators, because the space is translation invariant, and we describe all the operators as moving averages. And what is a moving averages is a measure applied to the function, but then you move it around. And if you don't like this position, actually say, I have my device and it's standing here, and I pull the function under this, and the value that you would take at the new position is rather what you take after pulling the function to the new position. That's why we have this t of x flipped, which is of course the t of minus x applied to the f flipped. Sorry, t of x flipped is t of minus x of f, and then flipped. Yeah. Okay, so now we have seen within, and we have a complete picture now within the bounded measures. First of all, discussing in the general way, we have the discrete measures. In the course notes, you will find more details about the fact that the discrete measures are not just the limits of the discrete measures and something obscure objects. They are just the absolutely convergent sums of discrete measures. So you would think these are measures which are sums of Dirac's, but the sums are convergent in the norm. And that actually translates into the fact that you're having absolutely convergent sums. So somebody is giving you a sequence of positions, maybe in the plane or so. You put a delta here, and if the sum of coefficients is convergent, then this is a discrete measure. And actually you can find some function which more or less has the right phase at these places, has maximal value 1. I mean, so that you deal with finitely many of them, and you find out the norm of such a discrete measure is really just the L1 norm of the coefficients. You can ask, what if I take limits in the norm, but then you rewrite this as telescopic sums, so you really get just a countable union of countably many points is countable, so you get another discrete measure. You don't have to think that in the limit you have something diffuse. But isn't this what we do with Riemannian sums? And the answer is, this is the big difference between approximation in the Waag sense, where you apply it, and there's a more general topology, and approximation in the norm sense. So this is really the big difference. The difference between the Riemannian sum and the, let's say, the Riemann integral from 0 to 1 and any discrete Riemannian sum is still very large. What does it mean? I can say, I think I have a very good idea. This is a so fine Riemannian sums with 3 million points in tiny intervals. It will be good for you for all functions. And then, of course, you can say, yes, if I only use differentiable function where maximal derivative value is 100, they will work fine or so. But I can fabricate a nasty function which is continuous. You can do an integral, but for that function, all your sampling points are all 0, but the function is not 0. The Riemann integral should not be 0. So it's far away from what we have. This is the distinction between individual action, that's strong operator convergence, or weak star topology, and norm. Then the next step was we had, in the classical approach, we have L1, and this was yesterday's main point, to find out L1 can be described as either embed the ordinary function, the test functions, continuous function with compact support, into the measures by saying I integrate my test function f from C0 against a function with compact support. Now suddenly we make ordinary function into elements of the dual space. We can measure the ordinary function in the usual way. We just take the L1 norm. We take the area under the graph, and that's some norm space. And we have seen that this embedding is just making out of ordinary functions actions on the C0 space, so these are distributions. And because it's isometric, and because the completion of any Banach space is uniquely determined up to isometry, we can say, I can take, because I like this approach, the closure of the test functions. Many of you will take Lebesgue space of equivalence classes of measurable functions. Other people can take other ways of equivalence classes of limits of Cauchy sequence. You can say, well, I like the Riemann integral. I have no problem to work with equivalence classes of Cauchy sequences of these test functions. And we will all talk about the same thing in a different way. We have the real number system. It's infinitesimals. It's Dedekind sections. There are many other. You can have other number systems. It looks different, but it's the same. So in that sense, we have inside the measures, we have L1. And because I have these pictures with the measure, so the discrete measures is now M with D with discrete, and L1 sitting inside, and the red box is my box for the bounded measures, which is kind of looking like the measures, but a little bit bigger. And then I thought, well, how can I give you an idea that they are approaching each other? So you cannot say there's a block here and a block here. In principle, you should do, because a discrete measure is completely, has nothing, if you say I have a discrete measure which is absolutely continuous, you're talking about the zero measure. So I should have two different boxes. Well, to divide the space into two pieces is not a good idea, because most of the things which are linear combination of these things are neither absolutely continuous nor discrete. And we have seen with the discrete measures we can approximate in the weak star sense everything. Every L1 function can be also approximated, but every discrete measure can be approximated by every L1 function can be approximated by discrete, and discrete can be approximated by Dirac-Gauss functions, for example. So I tried to make a picture and saying, if you think of the space of all bounded measures, inside you have the two classes that help you to understand what's going on. The traditional ways emphasize test functions, L1 theory. I tried to get as much as possible on the discrete measures, and that's where we can start from and where we can understand things. Just remember the formula that I call the fundamental theorem of Fourier analysis. In the L1 picture, it's f against g hat is the same as g hat against f hat. Engineers. In USA, I had problems to teach this course because engineers were telling me I cannot multiply a function of time against a function of frequency. But we are talking about an integrable function multiplied with a continuous function, which is the Fourier transform. So the integral of both sides exists, and Fubini tells you you can do it. In my case, I would say, how can I get it for discrete measures? Well, I have to know how it deals with delta. So I have to say, what is delta x applied to delta y hat? And we have computed in one line the Fourier transform of a discrete measure is just a character with a minus, because we are doing this e to the minus business. So if somebody says evaluate the character coming from y, he's thinking of e to the 2 pi I minus y, and then the argument is x. So the fundamental formula is you can interpret e to the minus 2 pi I xy, which is really the fundamental object in Fourier analysis, either as delta y hat at x and opposite in changing the role. And then you do it for discrete measures, but then of course I had to do some functional analysis, and I've not shown all the things, and go to the limiters. So that was one thing. So this was already this. I think I will try to show you only to remind you, because this was done yesterday at the very end. We can say it's not even necessary that now when we have measures and they are kind of multiplicative algebra. And the measures are mostly understood if you know discrete measures, so if we know what a single point or a single group element is doing. And we have seen already a collection of group operators where you have parameters, and each group parameter is giving you an operator on some spaces. The most important are, of course, translation. We have seen it. multiplication with characters. That's more or less the same thing on the Fourier transform side. But we also have seen stretching. I've mentioned rotation or so. So in harmonic analysis, such operators occur in great quantities. And then, of course, the action of a discrete measure, a finite discrete measure, even by taking limit, on a so-called homogeneous Banach space. So this is a space where you have the composition law. Rho is the law. And it's isometric, and you have a Banach space. So you can take limits of your Riemannian sums. That allows you to define an abstract action, and people call it the integrated group action. And most of the time, it's not done for the bounded measures as I do it here. So I choose a bounded measure on the group which is acting. But people would say I have an integrable function, and they write Bochner integrals. Essentially, they say, well, we write this integral maybe in a formal sense. It's an element in a Banach space. Maybe it's first an element in the Hilbert space. How can I describe it? Well, I think I should describe it in an orthonormal basis. So if you tell me what all the coordinates are in an orthonormal basis, I know what you're doing. So I would say, take the first component. How can I get the first component? And then I have a scalar Riemann integral, and I take the limit and say, okay, yes, this is doable. You do it for the second component, for the third component. Well, in a Hilbert space, you can do an orthonormal basis. In a Banach space, you can say, well, I take all the functionals. If I tell you what happens with all the functionals, I make the integral. This is the theory of Bochner integration or so. Measurable function with values in the Banach space. Then you're saying how to assign for every linear functional some number. Somehow you say, I would like to describe an element in Banach space, but actually you end up in the bidual space. So then you have to pull it down in the original Banach space, or say, yeah, but it can be approximated and so on. So that's usually a hard thing, which I learned, and I was using it for a long time. But when I realized this might be a better way, you're really just using two things. This is kind of these discrete measures tell you almost everything. And I don't go into the details. The point was, when you have two discretized versions of the measure, and you let them act. So it's like two Riemannian sums of some abstract object. You have to show that they are giving a very similar element in your Banach space, assuming that all the assumptions are satisfied. So we have to verify Cauchy condition. So if Riemann sums are fine enough, we are close to the limit. But we don't know yet what the limit is, so we say they are oscillating like a Cauchy sequence, and then there must be a limit. Now, the first thing is, can we verify the closeness? Can we verify the Cauchy condition? And the idea, I don't have to repeat it, but I can tell you, well, assume you work with two partitions of unity. Then you have a bump function here, a bump function here. If they are disjoint, you can throw it away. If they're overlapping, you take all the possible products. So you cut everything in pieces. Taking all the products for characteristic functions would be the joint union separation. So you have a covering, another covering, and all the lines separating these things would be taken. And then you say, well, in the one interpretation, the midpoint was chosen from the first family, psi I, and in the other it was eta j. But when do you use both of them with a given translation parameter? Only when these partitions of unity are close enough. And then you use the continuity of this mapping, so this property here, and you can use it in the same way as you prove Riemann integrals. You get the Cauchy condition. And then you have to do one little step, which you think it might be difficult, but it turned out not to be difficult. How can you prove that even in a Riemannian sum, a Cauchy net is convergent? And I tell this story sometimes because I think one can learn from it. I thought, now it's easy. I prove that a Cauchy a subnet is convergent, and if you have a subnet of a Cauchy net which is convergent, then probably the argument you can prove that the original net is also convergent. So if you have a subnet which has a limit, you know what the candidate is. The elements are sticking close to each other, so they will also be close to the limit. So epsilon over 2 argument. Now the only thing is, you should look up what the subnet is or so. It's a generalization of a subsequence or so, but it's not the idea that you leave out elements or so. And here we have an uncountable huge net. And what I would like to have, I would like to reduce it to a sequence. And then I was thinking about countability. No, you have to produce a sequence just as you do it for Cauchy sequence. I mean, you thin out your Cauchy sequence, you rewrite it as absolutely convergent sums. You do the same thing. The epsilons that you have, you can say I take epsilon 1/2, 1/4, 1/8. This is a sequence. That gives you a sequence of indices. So I'm saying if my Riemann sums are smaller than epsilon over 2, I have some quality. Epsilon over 128 will give a better quality. In this way, I produce a sequence, which is a Cauchy sequence. Oh, no problem with indices. A Cauchy sequence in a Banach space is a limit. It's not a subnet. That's the only problem I had, psychological problem. And then you prove in the usual way that if you have a Cauchy net, even the index set is good enough, which is close to a Cauchy sequence, which is convergent. It's a convergent Cauchy net, and it's just this usual way of proving convergence of Riemann sums. So this is a very abstract machinery, but we can, of course, also apply that machinery now to spaces that we know already. So we could say LP spaces. That's actually how we were proving L1 convolved with LPs in LP. You use the continuity of the shift. Now I'm saying this means rho of x is the translation operator. Satisfies clearly all the conditions. I think I don't have to repeat anything. And we can do only for p less than infinity, of course. We can do it even for measures, and we get the result. And we can say even p equal 1 is now a candidate. Now we have one more problem. We have seen that the measures are sitting inside L1, but now they have this external action. Purely logically, one should first try to distinguish. First, we were saying we're sitting inside L1, the measures. We have a multiplication which we call convolution inside the measures. Then we're shrinking it. We get a space of measures with continuous shift. So we could say we could take the measures with continuous shift. We call them abstractly B, and we apply this machinery. We have suddenly a bullet. We would write bullet. Here down we write regular representation, which means just shifting, and we get some new action. And how would you prove that they are the same? Well, probably you look up what is happening with the point measures. So if I take the translation operator, the rho of delta x is of course translation, which is what we had before. So the action of convolution with delta x is shifting to the left, or that's the same. So if it's the same on the discrete measures, by limits it will be the same. So you can say we can do all kinds of interpretations of the convolution integral. And especially, of course, that was one of the observations of one of my students who was getting an early version of these lecture notes. And he was saying, oh, that looks nice, but in the books I find another definition. You find the definition when you have a measure, two measures. What you have to do is you take the product measure, mu1 of x, mu2 of y, and you apply it to the function f of x plus y. And we have seen, well, if you have a bounded measure, you have another bounded measure, each of them can be decomposed into pieces. You can imagine that if I take a product measure, you can take the product of the partitions. So you cut it into little squares. So this is absolutely convergent. So even if this function f of x plus y, which is constant along the antidiagonal, is not going to 0, but it's bounded and continuous, this is meaningful. So to write, one has to prove it, but to write I say that mu1 convolved with mu2 applied to f should be something. You can write it in this way. Then, of course, you have to check whether this is the same, and the answer is yes, it's the same. But if you define convolution in this sense, again, you need Fubini and measure theory to get associativity, which is, in my case, for free, because associativity is okay for discrete measures, because there's associativity of operators. And so in this sense, we are on the safe side. So this is something I wanted to kind of add. And also because we have more and more other function spaces.
It's started coughing.
Okay, it's too, for me it's whatever. It's not. It shouldn't be too cold. Okay. Yeah. So the next thing which I took from a talk in Trondheim. So if you look up, if you would like to look up, I don't put it to the web page of the the course now. But you can at the talk server you can look for talks that I gave with the location Trondheim. Then you will find this. It was something about Wiener amalgam spaces. So we have seen the Wiener algebra as a very nice and simple space, which allows you to take upper Riemannian sums, and that's why this is very important. But I thought it might be good to give you a little bit idea about other Wiener amalgam spaces as they are called now. As you will see, I'm using two different notations. One is the two capital letters, and the other is with a local component in a discrete way and a global component. This has to do with the idea that I was explaining yesterday. If somebody is giving me a function, then in the spirit of what we will see also quite soon of a short-time Fourier transform, I'm continuously watching what's going on in the signal. So you might say, I want to know how much energy is in this segment of the signal, and now I want to see the development of the energy. So I'm saying it's quiet now. At this moment it's loud, and then it's like quiet. And in spectral analysis, we would even say now the high frequencies have a lot of energy, the low frequencies. But that would be a space which has local L2, global, and infinity. If the energy per time unit is limited or so. That's actually a class of signals that I think this local L2, global, and infinity, I think is a class that's quite important for practical things, because most of the actual signals are going on forever and ever, and to say they have to be finite energy, being at the beach here, I always think of this idea that I had long ago. I mean, this is going on. It's a little bit like something periodic, but not really in the mathematical sense or so, and it's going on. And only a tsunami says maybe this is out of infinite energy at some moment or so. But for decades, everything is local L2 and global infinity. Of course, when we deal pieces, it's reasonable to work with Hilbert space method because of scalar products or so. So, for example, you can say we can take, that's just a side effect. You can take almost periodic functions. That means you're saying, well, you have superpositions of periodic functions which are not synchronized. So that's, of course, something like the behavior of the moon or so. The word almost periodic comes from this is kind of functions which were studied a long time ago. They came out of fashion. I think now some people are still doing it. I think it's a very interesting concept. I would say in our construct this will be the Fourier transform of discrete measures, more or less. So if you have a discrete measure, it has a Fourier transform which is continuous. If you take a discrete measure sitting on the lattice, we will see it will be something periodic and vice versa. But if you just first say, I have some frequencies. I have the frequency of how the sun is, the Earth is going around the sun, and how the moon is going around the Earth or so. Then we can say, we look up in the calendar. When is the moon rising, today and then we say, is it periodic? And say, no, tomorrow it will be another time or so. But the definition, the formal definition of almost periodicity say, but the situation that we have today will be repeated almost precisely, I don't know, 3 years from now. So if you say, if you have a time interval of 10 minutes and you have a watching period of 5 hours, and we would like to see, well, what's happening today between 6 a.m. and 1 p.m., that's such a time interval, we can move in time and we'll find the situation very similar up to that epsilon again. For every epsilon, for every length. If you give me a long interval and a small epsilon, you may have to wait 10,000 years, but formally this is a definition. Then you can translate it and you can say, well, there is a definition of compactness in any Banach space. So also in the bounded continuous functions. And you can use this. It is repeating after a while to say, well, then more or less the shift parameter up to some epsilon you need only out of a finite range. I would say the mapping, taking a continuous, let's say uniformly continuous bounded function like the pure frequency, if you shift it, it will be a compact set as the image on of a continuous mapping on the of a compact interval on the continuous mapping. So if I need only things, you will find out these are compact set of translates. So if a function, and that's then the formal definition, going to the limit, making it a characterization. A function is called almost periodic in a mathematically more convenient set if you take the set of all the translates and it turns out to be compact, because that's equivalent to what I told you before. And then you prove you can find hidden frequencies, and you do a uniform approximation by the most important frequencies, and you get more and more frequencies. Maybe I will show you a little bit how to get these frequencies, because you take means, which means you are multiplying with very long rectangular functions. I would say take not rectangular functions, but maybe very long triangular functions. That means on the time side you are doing such things multiplied with frequencies in search for frequencies. That means fundamental theorem on the Fourier transform side. Somebody is saying, well, maybe there is an isolated peak. So maybe I put it here to mark myself. I search here with triangles which are getting smaller and smaller. This doesn't catch this, nothing. But if I'm at this position, I have a triangular function and you have a delta here, and I'm making it so small that no other frequency is hit or is relevant, because it may be infinitely many, I will pick out exactly this frequency. So this is a way of, in a an almost periodic function, to pick out the frequencies. This will be in the context of what we will do, because then they will have a Fourier transform, and that will be a discrete measure, and more or less also. Okay, so the idea in the classical way, there's a very nice survey article by Fournier and Stewart, which came out, I think it was 85, talking about the basic properties that they knew at this time. And at that time, there was no general local and general global component, but it was more or less LP theory. LP local, LQ global, and the sequence space idea is I cut into pieces and do it in a discrete way, and the capital ways I do it in a continuous way. And I call these descriptions continuous selective method and continuous discrete selective methods. The idea is going here, I thought, well, how can I explain it? It's how can you do a sculpture, so, or how can you produce a particular sound? I will give you two ideas which then relate to these function spaces. Well, people are doing a sculpture out of marble, would take a big block and throw away everything that they don't want, and the remaining thing is the figure. People in audio would take white noise and filter out so that what's remaining is the sound that you would like to have. Other people are taking material and gluing more and more together. They're doing synthesis. Or they're saying, well, we have a cheap synthesizer who is able to produce this tone, and then we have this electronic organ which is obtained by synthesis or so. And so I'm saying I can describe these amalgam spaces either by saying we're starting with a universe of all reasonable functions. Now, if my local component is local LP, of course you would say it is not meaningful to start with a discrete measure. I should start with functions which have the property on each interval they are LP. So that's the local, the kind of the continuous description. I would say I measure the LP norm at every position, and then I take the good ones are the ones where the global condition is in the second component. Sometimes people also put the global component in front, so they say it's a sequence space with vectors. Maybe it's better here. You would say maybe instead of LW local, L1 global, they might write L1, L infinity. I would say this is quite reasonable if you think in the synthetic way, because how can I get such a function? Well, I put an L infinity function here, another here, so I fill the boxes. Even if I'm a bit generous, if I put a slightly broader box here and do the same thing, then you would say, okay, when I measure it, I have to cut it into 3 pieces. I get something which is equivalent. So, but discrete synthetic is putting things, and I think this is for me the most natural way to understand what operators are doing. Linear operators on the linear vector space, if you know them on the basis, we know what they are doing. Function spaces which I can describe by these atoms, in this case it's quite general. It has to be something in LP living on an interval of length 1, because that's the building blocks. And I glue them together, and I want to know what they are doing, and then I can handle the case. Now, there is also a synthetic way of interpreting these norms. So I can say instead of analyzing from L infinity local, I synthesize from L infinity. And there I have another kind of realistic picture. In the old days, when they were building highways, at least in Europe or so, this was made out of concrete. So how do you make the highway? You have, I don't know, some rectangular area, you put it, and then you have another area, and you put it, and you put it. Nowadays, you have asphalt. You have a big machine, you're filling in, and while you're moving, you're doing it. This is synthesizing this function. Of course, you can do it by vector-valued integration or so. I find this method kind of, I would say nowadays I call it an elegant method, and I know that it's equivalent to the discrete method, but I mean this discrete pieces gluing together is what you makes understand everything. Also the discrete way of measuring, I think, is more natural somehow. I took this intuition, and that's the first few pages of that talk, from interpolation theory. So interpolation theory is a method to make out of two Banach spaces intermediate spaces. So you can make out of LP spaces, you can make the so-called Lorentz spaces or so. And there, it's again, there's a K functional that tells you I have in the universe of, let's say, in the big, small in the big space. In the big space, I have certain quasi-norms or semi-norms or norms, equivalent norms. And if the family of norms which makes some component more and more expensive is exploding or not in a function space, then the things are thrown out. And there is a J method which says I'm rebuilding from the small space. I'm adding elements which clearly are in the big space, but I'm allowing only certain linear combinations. And I found a book of Butzer and Scherer, which is unfortunately only in German language or so, where they show you can do this K functional theory in a discrete or in a continuous way. I mean, normally it's described in a continuous way. So then I thought, oh, their parameter t is a positive parameter. And they are either taking the discrete stops at 2 to the n, or the continuous integral with some dt over t. And that's where the harmonic analysis training was helpful, because when I see R plus with measured dt over t, I say, oh, R plus as a multiplicative group with dt over t. That's isomorphic to through exponential function to R with addition and ordinary measure. And intervals of equal length correspond to the adic wall. So kind of when they do it in a dyadic way on R plus with Haar measure, I will do it in an equal way, and that's kind of was a little bit inspiring me in this work. Okay, now I will see what I can do quickly. There are very simple results about duality. So in the usual restrictions, avoiding the infinity case, you can, or most of the time you can work component-wise. So you don't have to check the details, but you can use them, well, from tomorrow on. So the dual spaces are this, and I find this version of Hausdorff-Young quite interesting. So you say a function which is local in LP and LQ, both parameters satisfy this condition that you expect. Under the Fourier transform goes into a space which is also described in the same family, but the local properties of a function, roughness, tells you what the global properties are. Therefore, the p parameter here is giving you the p prime parameter, the conjugate index on this side, and the global behavior, let's say good decay, better good decay, give you something like this here. So very interesting special case is, of course, if you would take L2 here, then L2 p prime is L2, so I have this here, and L1 here, and then you apply Riemann-Lebesgue or so, you get L infinity, but actually you're getting the closure of test functions in L infinity. So you can say if I take a function space which is local L1 and global L2, then its Fourier transform, switching the roles and taking duality, is local L2 and global L infinity. And these are the spaces that I mentioned in the beginning course. When you prove Blancherel, you are saying I'm having L1 and I'm having L2. So clearly L1 plus L2 contains everything which is local L1 in an interval. So among the amalgam spaces, local L1 is okay. But globally, L1 has decay. L2 has a weaker decay. So I take out of, so L1 plus L2 is a strict subspace of local L2, local L1. That's the largest space local on the torus. L1 is bigger than L2. And then I'm going to the sequence space, and that's L2 is bigger than L1. And I still can say, now it's not just a locally square integrable function, but it's square integrable, and if you move your window and you measure the L2 norm, it's uniformly bounded. Now, for me, and for various papers I've written, now I've forgotten to start this, I guess. Yeah, of course. For me, the convolution results for amalgam spaces have been among the most useful things that you can think of. It's essentially saying if you have three spaces, then they all have local components and global components. What you have to do is look at them in the local component and in the global component. If you see that the space is made up with P1, P2, P3, then you have to make the parameters such that the convolution products of LP functions from LP1 to LP2 go into LP3. And the same if you have global decay properties with the weights such that this is true, you get the compound result. Now, things are already getting complicated because you have many parameters or so. And then you can say, why didn't you put weights in the local component? I would say because weights should be relatively smooth. They shouldn't be put in the local component, because if you have a weight in the local component and the global component, you should be able to pull it out and only see a weight as something affecting the global component. So it's just more complicated if you allow it in both parts, but it's what you have. And if you don't like weights or so and just want to know what happens if you are taking L1 and L2 just as an exercise. If you convolve amalgam space L2 global L1 with amalgam space local L1 global L2, so you just flip the positions, then my argument would be, okay, in the one component I have an L2 with an L1 space going in L2. In the other space they come up in an opposite direction, but doesn't matter, it's still something from L1 with another L2 is L2. So I'm ending up in L2 local with global L2, so I'm ending up in L2. Later on we will see when we do sampling, you're sampling and getting a smooth function, you're sampling, you're getting a discrete measure. A discrete measure is not in any of the LP spaces. But then we smooth it back, and then the idea is, while sampling should preserve the global structure, it destroys the local smoothness. A band-limited function in LP is smooth, and it's in LP, of course. If I sample it, I get a sequence of coefficients in LP, and I will say, no, I'm getting a discrete measure which is in a space of this type with local bounded measures in global LP. If I convolve it back, I have a measure multiplied to convolve with a smooth function, and it's fine. So this is something we will see in many places. Yeah, maybe this was one of the reasons why we were using it. This is more for the talk. In the regular case, you can say these results and the partitions of unity which come up are so regular, and you can maybe help yourself with Poisson's formula. But if somebody says, for example, I have something between, I mean, let's say we look at the real, to give you an idea. We look on the real line, and we have a discrete measure related to some sampling procedure which tells you I have something between 3 and 12 points in each interval. And we sample this. And then we do some procedure and say, well, so we put Gauss functions with these amplitudes at all these points. So we have a sum of Diracs and replace them by Gauss functions. So we have to see how can we give a control on a sum of translates of Gauss functions with irregular shift parameters. And then the answer is, I just have to see that if the point set is well spread, and this is here, so you have to look at this. You're looking at the density of the points in the plane. I would say I have such a looking glass, and I count the number of points or the total mass in this window. That's the measure norm in this. If this is uniformly bounded, then I can convolve this with everything which is in the Wien algebra. And of course, Schwartz functions are in the Wien algebra. And I'm sure I'm getting something bounded. Just imagine you would have to say, well, somebody tells you, here's a collection of Diracs. These are amplitudes. And at each location where you have a Dirac, you have to put a Gauss function or a bump function, a nice decaying bump function. And that bump function has to have the amplitude of your Dirac. And then you have to control that this sum is the total sum is well defined. It's giving you a bounded continuous function. Then you would say, okay, now how can I control the value here? Okay, probably it's all these neighboring Gauss functions. They have an influence. They're very far away, but they're infinitely many. So you have infinitely many pieces or so. And then it's very good to say, well, if I compose my Gauss function into an absolutely convergent sum of little bump functions. So imagine you would put at every point where you have a Dirac just, let's say, a kind of smooth rectangular function. Then I would say, okay, how many points are in my neighborhood? The number of influential atoms is finite. And then I would say the effect of this thing here is harmless. But then you say, well, but you also have atoms sitting, I don't know, at position -10. Then I'm saying, okay, here I can control everything. Now I go to -10. I take the building block which is -10, but I do the same thing. So I have a control over what one layer is doing. Then I add up all the pieces and I can do it. So it's kind of a way of implicit atomic decomposition that allows us to I don't go into more detail. So that maybe this is the story. If somebody needs a linear combination of shifted versions of some nice function, then we are always rewriting it as a discrete measure convolved with that function. And for example, in Shannon's theorem, that G could be a function which is such that the Fourier transform reproduces your spectrum of the band-limited function and going down fast enough, but in a smooth way, so that this guy is in, I need Wien algebra, local C or C0, global L1. And here you see very nicely how you can get it. This, if the points are okay and the coefficients are in LP, this is an element, in my view now, in the amalgam space with local structure bounded measures, thinking of discrete bounded measures, global LP. This is Wien algebra, and I say, okay, we have learned measures convolved with continuous functions to continuous functions. And either you have a continuous description, then I would say L1 convolved with LPs and LP. But for containment relations, it's better to think in the discrete way. Then I say, okay, if I think of L1 now convolution on the discrete lattice, L1 of the integers convolved with LP of the integers is LP of the integers. So that's how you get such results. The other thing is, that's also here, you can say, I have a function which is smooth and in LP but smooth. By such a relation also, which I skipped now, you can say it's actually not only smooth, but it's even if you take local maxima, it has this property. So this is a kind of cheap, simple version of the maximal function. So whereas I was taking the maximum interval-wise, I can take the maximum over, kind of I have a bar, which I slide over the graph. So at every moment it's the maximum of the interval, and it goes up and down. And so if that is good, then I can say, well, I can multiply this with this Dirac comb, with this sum of deltas. So you would say, I'm grabbing the values. So I'm making now a list where I'm saying at this position I have this sampling value. Now I'm saying, no, if we have not written it down, but I think we just should recall or you should look up. I'm using the following simple statement. We can multiply arbitrary measures with functions. So the rule was multiplying a measure mu with h means to take the action of mu and let it run not on f but on h times f. And if you do that in one line, I don't want to go to any blackboard now, you apply it to a Dirac, you find out multiplying a Dirac with a function is just sampling the function value and multiplying on the Dirac. So h times mu on an individual function, of course, there's a typo, h equals f here. So it should be h of xi times delta of xi. So when I have this sampling procedure, my view is knowing the sampling position is the same as a sequence of deltas, and I multiply it, I get these weights. And so when I start reconstructing, very often we start with this property. So somehow, if you have information that the smooth function in the cubic spline type space or so, or in a band limited space is in this space, you sample, you go in this space, and with these convolution ratios you can come back. So this is why these these function spaces are okay. Okay, very good. I forgot, that's actually something I was looking for, the definition of a homogeneous Banach space. So LP spaces are one example, the Wien algebra is another example. All the LP-LQ spaces with P and Q less than infinity have these nice properties that they are translation invariant Banach spaces. So the rho is now the translation. The whole reservoir is local integrability. And the only thing is you have to assume, this is what you find, for example, in the book of Katz-Nelson. This is a definition from the book of Katz-Nelson, that the embedding into the space of local integrable function should be continuous. But I think of the local integrable function as the absolutely continuous part of the Radon measures. But it's, in this case, it's the same. So you would say, if it's local integrable, I have a family of 7 norms. You can integrate over this interval or that interval. Any compact set allows you to integrate. So, and the embedding should be continuous. That means if you are giving me a compact set, then you should be able to control the compact set, the integral over the compact set by some constant depending on the concrete compact set times the norm of the space. So it just avoids, I would say, artificial things that somebody says, as a mathematician, we have a lot of tricks or so. Well, I can define a strange Banach space, and I can identify it by some abstract mapping with some function space. So it is a function space, but so that these embedding are discontinuous. Yeah, I must say, even if I have never cared about it, and I think I have not seen even one example where this doesn't work or so. But if you would leave out the condition, probably somebody could make up a nasty example that is useless. So in that case, all these function spaces with this simple property have the property that they are acting, that L1 is acting on it. And that's the point where I'm coming back to the definition of Siegel algebras. Siegel algebras I learned as a student from my advisor Hans Reiter, and I usually say Hans Reiter's Siegel algebra because Irving Siegel did not know what a Siegel algebra is, probably very much like Hilbert was not aware of the Hilbert space. He was working with the unit cube of the Hilbert space, but not as a vector space with a norm. Okay, so Hans Reiter's definition of a Siegel algebra is, in the modern terminology, you're sitting inside L1. So if you're sitting inside L1, continuously embedded as a Banach space, it's clear that you are also having this embedding into the larger locally integrable functions. You have a norm which is isometric invariant, that's somewhere hidden in the text, and shifting continuous. But then he also says, and it should be dense. So essentially, I think he wanted to exclude something like a closed ideal, all the functions in L1 where the Fourier transform is vanishing on an interval. That's a nice closed ideal, but it's not a Siegel algebra, and that would not count for him. And also clearly people in approximation theory, the people who would like to describe smoothness, so that's kind of when you want to get into more details about what does smoothness mean, approximation by trigonometric polynomial. They were working a lot with these homogeneous Banach spaces, very often first on the torus, then on the real line. So you can say, if you give me a Biesov space, they are also in this family, because what you're doing is you're describing the smoothness by modulus of smoothness. So you're saying, I have an LP norm, but no, not only it's going to 0, but it's going to 0 in a certain speed. And then you check that test functions have this property. Test functions are dense in Biesov spaces, whatever these spaces are, and you can show that L1 convolved with elements of a Biesov space is okay. So that's why I wanted to mention this. Also because we will see a very specific algebra. Sorry, that was the wrong direction now. Yeah, something that will come again and will be a late situation, but since you have seen tempo distribution or so, we can of course already talk about what I have been calling standard spaces. And again, you should, or you can try to look up, but you will find different uses of this. So standard spaces is not a mathematical notion, but it's kind of, you would say, something that you find very often in your everyday life. And of course, for you, that might be something different from what it's for me. But even for me, what was standard, I don't know, 20 years ago is not standard now. I would not do things regularly in the same way. So I'm thinking, these are the function spaces. These are general properties that I find useful. So I learned more or less many of these things from Triebel. Professor Triebel has various books about function space theory. And what you learn then is, well, you're dealing with function spaces. But when you are using function spaces, you need the dual spaces. So for them, they are going beyond homogeneous Banach spaces. They include dual spaces of ordinary function spaces as well, and they also call them function spaces. And I've taken this spirit. So essentially, people who would say we have tempo distribution also use the word generalized functions. So if you say somebody has Banach spaces of generalized functions, that's really the thing that I want to have. Now, coming from the spirit of Hans Reiter's signal algebras, I'm saying, well, that's kind of my choice, and one shouldn't take it too serious. I like to study function spaces on groups because kind of I'm in harmonic analysis by dedication or whatever. And I start to be more interested nowadays also in function spaces on domains. And I recognize that people doing PDE cannot always work without boundaries and infinite domains or so, or at least they don't get the main point of differential equations. So we're really trying, we have a new project now where we try to start to work with function spaces on domains. And of course you have Bezow spaces on domains, and so it may be a difficult business, but until now I was restricting myself function spaces and domains, and I would not like to say the functions which are zero on a big interval again or so. I would like to take all the Schwartz function, all the good ones should be inside, and they should be decent objects. Maybe tempo distributions, later on I have a different thing. Now I also don't like function spaces which are not translation invariant and are not allowing modulation, so this means they're invariant. Again, in this setting, you are not assuming that they are normed, of course, if they are Banach spaces, but the norm does not have to be isometric. So weighted L2 spaces are good examples of this type of spaces, because weighted L2 spaces normally have weights of the form 1 plus x squared to some power. If you shift, you can control the norm of the shift operator. Every individual shift operator is invertible, has a norm. And it's about depending on the growth of the weight. And then the only thing that you have to change is then you do the same trick. I mean, you have the same row, you can do the same representation, but then of course there's a price for shifting. And the price is compensated by restricting the attention to weighted spaces. So you have a Berling algebra. So every shift parameter can only be controlled if the coefficients coming with the shift parameter multiplied with the weight responsible at that point, and that has to be submultiplicative, is okay. But the rest of the proof is the same. So you do the same thing. You can say even the bounded measures of this, and one even can say in the L1 case, you can have Wendel's theorem. The multiplier, so the operators commuting with translation from L1 to L1 are the bounded measures as well. If you are interested in the Berling algebra, what are the operators L1 with weight to L1 with the weight, and you find it's the measures with respect to the weight. So it's fitting quite well, and I think I will stop using these slides and start to go to what really will be the point that will be more or less, can tell you already from the very beginning, it will be a signal algebra which got the name S0 in '79 when I discovered it, and which will be the starting point of these things. And nowadays I think one can say and sell it as something that is relevant for time frequency analysis. I think I will skip most of these things. You have seen such pictures already. Yeah, maybe because I have it here, I will tell you a little bit again these symbols about function spaces and how the spectrogram comes in now. So this is my symbol for a L2 space, and now this is a spectrogram, roughly speaking. So energy distribution, and I would say if you give me a random L2 function, the spectrogram will be spread out. It will have kind of equal energy at all times, at all frequencies. It's actually very nice if you look at this. If you look a little bit closer, it looks as if there were blue dots. And the blue dots are the low energy regions, which are more or less the zeros of the short-time Fourier transform. And then you will find out you have exactly n such zeros, and they are spread out randomly but uniformly. So it's like a uniform random number generator that you could create from this. I'm not sure, but I think that's the idea. Now, if somebody tells you that he has a spectrogram which looks like this, and you can really now take a piece of music or look at different pieces of music, when will it look like this? I have to tell you, this is the time axis at 0 in the middle, and so away from this axis is the frequency axis, and so away you see a lot of blue, which means there is not much high frequency component. So what do you expect? What does it mean for the function? If you don't need high frequencies, it's smooth. Yeah. If you would have a band, could do a band limited function, you would see a stripe. So it's kind of a stripe of the width with maximal frequency, but because we are localizing it, it will have a smeared effect or so. So something which has rather diffuse things is a space of smooth functions. Now, I thought we are getting Sobolev spaces by smoothing an ordinary L2 space, which means we were shrinking the frequency component. That's why I thought this could be a good symbol for a Sobolev space. So the blue guy is the Sobolev space. The next one is the blue guy is a Sobolev space, and now what is the yellow guy? Well, we do the same thing that we do for a construction of a Sobolev space, but now on the time side. Well, a Sobolev space, let's say the functions which have two derivatives in L2 are the ones where you multiply with 1 plus omega square, and that's still L2. So now we are multiplying with 1 plus t squared, and we are making the time decay better. That's why it's an ellipse which is much more slim. And I'm using this to tell you, well, our space will be a little circle inside. And of course, what I'm trying to do with these pictures to tell you something that you should expect by just remembering pictures, whereas I was getting some, or we were getting some results, and these results were used to motivate the pictures. But I think everything fits together at the end very well. I'm not sure if I have it like this. No, I don't have. Yeah, oh yeah. Something in terms of inclusions, I can make such a statement. So I can ask, first of all, the following question. In terms of pictures, you give me a circle of a given radius, and of course I had to adjust all the parameters. And then you shrink the ellipse such that it's narrow enough, and then you shrink the other ellipse. When can you reach the point? So clearly, the higher the smoothness is, or the decay, the smaller the intersection will be. So eventually it's clear. So the point is when it is the critical moment, and the answer is when you have the decay parameter, the growth in time and in frequencies now separately. Sobolev space is using symbol decay in frequency with L2 norm, and this is ordinary with the polynomial weight. If this is larger than d, then you are inside S0. There are some asymmetric versions. I don't think I will talk much about this, but they would say, well, I could, for example, have lower smoothness here, and then I could compensate by increasing this. So there are Charlie Gröchenik has a paper where you find these details, where you can even say I can have a LP space with weight on one condition and then Q space on the other side, but if together they are reasonably strong, then it's working. Now, an important and interesting point is this space S0, we will see it's sitting inside the Wiener algebra, so it consists of continuous and integrable functions. So I can let this S parameter go below D, and I can make up by better decay or so. But what if my parameter S is getting less than D over 2? That's now a question to those of you who have learned about Sobolev spaces already and the so-called Sobolev embedding theorem. So when can you be sure that a function which has an abstract smoothness, so its differentiability somehow in an L2 sense, is really an ordinary function? So the Sobolev spaces are getting smaller and smaller, and at one moment they're getting inside the continuous bounded function. They're actually getting inside the Fourier algebra or so. And that's the moment when S is larger than D over 2. So there's only the interval S between D and D over 2 where you can compensate it. And why do you not get anything below D over 2? Well, below D over 2, you are having functions which are maybe in the Sobolev space. These guys may be discontinuous. So if somebody says, I have found now, because your smoothness requirement is not good enough, it's differentiable in an abstract sense within L2, but it's not continuous. Then I take a discontinuous bump function, and then I say, what kind of weight conditions can you put such that this makes the bump function smooth? And you can put arbitrary weights. This bump function is sitting in the interval from -1 to +1. It doesn't see it. It is not influenced. So increasing the weight only makes sense when you have already a minimal amount of smoothness. And when you want to have a balanced situation, I think that's maybe something that's kind of good.
1 minute actually.
Yeah.
So even on the abstract groups, we can do all these things
Yeah.
without getting into the differentiation part.
Yes.
And without getting into the Schwarz space, we go for
Absolutely.
Schrödinger algebra S0, and we get the thing done.
Yeah, I know this is also true. Then you would say it has to be the inverse of the weight that is in L2 or something like this, which corresponds to, this is kind of polynomial weights, of course, you know. If you are in RD, or let's say maybe you're in the plane, 1 is the function 1 plus absolute value of x squared integrable or so for which exponent or so, and you have finite volume or so. That's quite, I mean, in the one-dimensional case, it's just really, you have to remember 1 over x is just slightly too slow to be integrable. 1 over x to some higher power will be integrable, lower power will not be integrable from 1 to infinity. That's kind of, and then you rotate everything, and then you know what's going on. Yeah, that's another picture where you can see if I choose a pair of ellipses, when is the intersection of these ellipses inside the red area. So the red area is now the S0 space. But you can also say now we have lost an important property. This is kind of, we're talking on the surface now. This S0 space will not allow differentiation. But you can, of course, also make versions which are smaller than, so that you get from a smaller version, let's say the little circle here, into a bigger one.
Then how do we deal with smoothness then?
The smoothness will come into decay on time and frequency. So I will say I will take locally FLP with the weight and globally LQ with the weight. So this is the idea. So we'll come to the pictures with time frequency analysis. Well, maybe I skip this. Yeah, so kind of in the long run, to mention it right now, the goal will be, we will talk about now the yellow guy is red, L2 is red, S0 is inside, and the S0 prime is the outside world. And I will very much use the analogy between rational, real, and complex numbers. So inside, everything is harmless. You can do integral transformation, inversion, everything is fine. At the L2 level, you can say it's unitary and everything is fine. But even already Plancherel is telling you, you cannot define the inverse Fourier transform of a sinc function through a Lebesgue integral. And that's at the level of pi square. I mean, you reduce it a little bit, go over, and you reduce it better and take limits or so. But if you want to understand what the Fourier transform is doing, I think you should look at the MATLAB experiments. We're looking at the FFT, we're having the FFT matrix, and then we have explained we take square root of the FFT matrix or DFT matrix or so. This is a unitary matrix. What are you learning from a unitary matrix? You're learning it's a base of change of basis. From that xy coordinate, you would like to look at different angle, you choose this orthonormal basis. So it's a change of basis. So what are the unit vectors? Okay, and that's where physicists are or engineers are saying, we are changing from the continuous basis of delta x to the continuous basis of pure frequencies. And then I'm saying, trained in functional analysis, sorry, I mean, the deltas are not in L2, and you're saying it's an orthonormal basis, but how do I get the coefficients or so? And then we are suddenly in this situation, and we call it a rigid Hilbert space also, where you have a scalar product. I mean, and at the end it's like LP space, sequence spaces. You're saying L2 is the infinite dimensional version of Rn. So L2 vectors are good, they have scalar product with angles. But then you come with constant sequence or with a pure frequency or so. Can I take the scalar product of a constant sequence with an arbitrary L2 function? No, I cannot sum up constant 1 against itself, for example. That's why we have to introduce the integrability in the continuous setting and the L1 condition. So we're always, when we have this pairing, the pairing is the main point. If we want to be symmetric and our objects are either row or column vectors, as some people say, or they are used to constitute functions or they are constituting measurements, we're happy to have the Hilbert space because that's self-dual and we have Riesz representation theorem, and there's no distinction between this object. We say the Hilbert space, we have all objects. Oh no, we use this vector in the Hilbert space to produce a linear functional. Oh, you have an abstract linear functional. I have just to look up what the vector is generating this functional. And now we have to look more closely. Maybe we look at the functional in the little space, then we have something on the big space and so on. So, and these three layers will be used continuously. I'll leave out these things. Yeah, because there was some demand I wanted to mention. I will later on also discuss a little bit about two-dimensional time frequency analysis. And then essentially the question is, what is two-dimensional time frequency analysis? So you do a local Fourier analysis in 2 dimensions. What are the building blocks of 2 dimensions? These are, of course, abstractly speaking, the product of pure frequencies in one and the other directions. So to make a little model, make a sinusoidal function in this profile and another sinusoid in this function, and then connect it linearly. You will see a plane wave. And the plane wave, of course, has a ripple frequency which is high, which is fine ripples, or coarse, which is low frequency, and it will have a direction. So you find out the frequency domain is again from the real line, it's from, you go from t to omega, and then image processing, you go from image domain into wave number domain. So you're having a Fourier transform, and I would say in the Fourier transform of that picture, these stripes, which have a certain frequency and a certain direction, will be quite dominant. And as you can read scores, you can also say, well, I can even predict, I've not done it here, but I can predict somehow where the peak of the two-dimensional FFT of this viewed as a a color image, but taken as a black and white image will be. It will be in the normal direction of this because the vertical strips are very, very strong, and it will be at relative low frequency. So my spectrum will be again a matrix, and I will go in rows and columns in a direction mostly horizontal because the stripes are vertical and not far away. That's where maybe this spectrogram will have a peak. Actually, most black and white pictures will have a huge peak at 0, because if you have a random picture with gray values between 0 and 256, you will see the 0 component, which is the integral, which is the sum of the pixels as the value corresponding the coefficient at 0. So people call it the DC component. So if you really you can do it in MATLAB, you can get a huge value. You look at this and you say, oh, I cannot see anything. Well, this is because MATLAB thinks if you have a picture, let's say with one value 3000 and the remaining value between 1 and 100 or so. And it says, well, the range is 3000. I have to divide it into equal pieces, translate that into gray values. So I have 3,000, 2,950 or so. So almost all the values are so the whole information that I would expect in the image is in the first 3 layers, and they are almost the same black or white or so. So what you have to do is compute the 2-dimensional FFT, take out 1 pixel value, which is the 0 component, which is of course at coordinate number 1, 1 in MATLAB. And then you will see, usually if you take the absolute value of this, giving you the information that I was indicating. Now, I think there is not much more. Oh yeah, okay. Now actually we can go into this. You have to tell me when I should stop, but I think we have some more pictures.
5 more minutes.
Yeah, that's good to get an appetite for the mathematics again. So this is an old standard picture that many people attending my talks have seen already. This is really was in the early days I was recording some piece of music. It was a piece of a Beethoven sonata, and really with MATLAB computing this spectrogram myself. So what are you doing? Of course, you're taking something like a wide Gauss function, and you're taking FFTs for that wide Gauss function. But what you can see is the time structure is this. So if it's a piano thing, then probably the pianist has hit the key at this moment. So that was the speed, how things were going. And you also see that here things are going down. So nowadays, I would say one should look at the gabarator that's much more refined or so. But already here from this, you can imagine that this the melody is dee da 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 dum. So it's kind of a waterfall from higher to lower. So dee da 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 dum is the melody. You can also say what's going on here. And of course, it's going on resonance. You see one score, maybe you see an accord actually, and then you press the keys, and then the whole system is starting to vibrate or so. It's 3 strings per tone, so an accord with 3 tones already has 9 things which are moving, and that has resonance with the other overtones or so. And you can do some training and do these spectrograms such that you recognize, oh, now it seems that probably this looks like a flute, and this looks like a piano, this looks like that instrument. And you can even do what Monika Dörfler was once doing with her group, some morphing. You can say, what is the sound characteristic of an instrument, maybe nearby instruments like saxophone or clarinet. And then due to the physical laws or so, I think one is half, I don't remember the details, but I think it's like this. One is half open and the other is open, or closed. And therefore, in one case, you do not have all the frequencies. So let's say the even frequencies are not here, but the odd frequencies are here. So you can go to the spectrogram and say, take away the things which make the characteristic of that instrument. And then it sounds more like, let's say, from clarinet to saxophone, assume. And then, of course, you can do a smooth transition. That's like morphing. You have a picture of one guy and another person, and you try to do something and interpolate, and now it looks like 80% the first and 20% the other, which I think is interesting if you do it carefully in cooperation with people in music or so, because they're always eager to have some nice sounds or to put things together. So the standard definition, and we're entering this field now, of time frequency analysis is all the things that you can do with time shift, frequency shift operators. We have the main spaces already and the first thing is to do the short time Fourier transform. That's what we just have seen. And the explanation is very easy. We had already all the operators. Just recalling, a frequency shift or modulation space is called like this because on the Fourier transform side, if you first take the Fourier transform, it's an ordinary shift operator. But then you're having, and that's so to say the idea, I'm thinking of the spectrogram being already computed. And I'm kind of half blind moving around saying, where is a lot of energy? I'm measuring. So what you're doing, we're moving our sensor, which is typically a smooth function, centered at 0, real value, so that the Fourier transform is also like a bump function. And very often people argue that one should have minimal uncertainty. That's why one should use the Gauss function. I would say it's depending on the application. because I would say if you don't have any preference, so if you are not in a situation where you want to analyze low frequencies in a musical recording, where you need long windows, it doesn't make sense to choose our Fourier F15 invariant Gauss function. That would not be long enough to do this analysis. But if you have no other thing, then of course the Gauss function is very good, and for theoretical reason is even better. So we call it, following some terminology which was already established, the name voice transform. So you can say I'm describing in this line the short-term Fourier transform or the spectrogram with respect to a window G, which is kind of the moving window. And the argument usually is you take a function f, this is a long piece of signal, or it's a big picture or so. And because it is not meaningful to have the overall FFT of the picture, you look at the patterns locally. Now we are moving over the group. Every locally compact abelian group, you can do it. Then you have frequencies, the elements of the dual group, the characters. Altogether, in the discrete setting of the cyclic group of order n, we have discussed in the MATLAB session, so to say, we are getting n squared such elements. That's the full spectrogram. I call it spectrogram, but maybe it's not completely correct, because sometimes people, when we plot this, and you can describe it, it's just another name, as time frequency shift. So pi lambda is just by definition combination of first the time, then the frequency shift. Some other people like to have it in the opposite order, is no problem. And sometimes I even have a shorthand notation. Instead of saying I move my atom to this time position and frequency position, then I call it G lambda. So it's the bump at that point lambda. So I have a point, and that's here. And so the set of all these color products is giving me these pictures. Now, when I plot it, I don't plot real and imaginary parts separately, for two reasons. First of all, it's easier to have one picture, therefore you take the absolute value. Secondly, each of them is really highly oscillating, and these oscillations, to our knowledge, have not a big meaning. So why should I worry about two pictures which are both very, very wiggly, so to say, but we rather have one? So we have numbers which are in a certain range. Actually, if I say for convenience I can normalize both of these functions, G is normalized in L2, F is normalized in L2, then all these color products by Cauchy-Schwarz will be bounded by 1. So the absolute values will be between 0 and 1. And then to say it's big or it's small, I can take the functions or the square values. That's not a big problem. So sometimes people call the absolute value square the spectrogram. I think we are just sloppy and use, short-term Fourier transform is certainly this function, and we can use this. Some people call it a sliding window Fourier transform and so on. And here in GeoGebra you can look at how it behaves. That's not so important. I will stop with this slide by saying the size can be controlled by Cauchy-Schwarz. That's what I just said. But now another key property is this one, this isometric property. If you take the G especially normalized, then this F is normalized, giving, let's say this is unit L2 norm or unit energy. Remember, engineers say the energy is the L2 norm squared, or just the integral of F absolute hat. So if it's normalized, if it's 1, then 1 squared is also 1. So if both of these things are 1, then also this squared short-term Fourier transform in terms of absolute value is something which is having integral 1. And I think it's a good picture, because it tells you we have unit energy in our signal, and therefore the spectrogram is having unit total mass. So we have a probability distribution that's telling us how the frequency is distributed. And that frequencies can be distributed in a certain way. And just to give you a rough idea, it can be concentrated more in that direction or more in that direction. But it can never be a Dirac. There's no way of having all that information in one point or even in a small sector. So that's one of the principles coming from uncertainty. If you think again in musical terms, I find it quite plausible and beyond all the mathematical estimates. If somebody is giving me a tiny little part of a huge sinusoidal function. So you have something, the sinusoidal function is stretching over the whole table, and you get this little piece. And then you are asked, was this frequency 0.0 or 0.1 or 0.12? It's ridiculous. It is not meaningful to talk about low frequencies if you don't have a few oscillations, let's say at least one or so. And so in that sense, this idea of time frequency picture, it's okay, but everything is kind of blurred, and it depends on how you look at these things. And another thing which I would like to mention before going to break is people always say you never can determine both the time, position and momentum or so. Here in the frequency spectrum, you can never have both a good resolution in time and frequency. But the correct statement is, whatever window you choose, you have problem either in both cases, that's possible, or in one direction. When you choose a window, I can tell you what kind of problem you have. If you say, I'm using one window to determine the frequency resolution, and those places where it's reasonable, where you have sustained tones, and you choose another window to find out the changes, then you can do it. So with several different windows, you can do it. And it's nice to compare it with radar. So when you have radar, if we think of a civil application, you can have the airport, and they control the landing, the machine which is landing. They're sending out things, and they are correlating what they send out with the receiver. So they are exactly doing such things. And what are the two effects? Or what they want to know is, of course, where's the machine, how fast is it going? And so they tell it, well, please slow down, please go deeper. So that's a good automatic landing, soft automatic landing. And now Heisenberg says they cannot do both of them. So kind of, if I only know the speed and don't know where the machine is, it's very bad. So of course what they do, they send out pulses. These pulses are reflected. You find the running time and say, okay, it's still away 2 kilometers, still enough time to make arrangements. How fast are you? You're sending a Doppler effect, a pure frequency, kind of, I would say, a plateau function with a long window. It's reflected, and because the machine is arriving earlier, the reflection is coming back a little bit faster, so you have a Doppler shift. So the current speed of this, it takes a little while, I mean, probably 100 milliseconds or so, and then you know how fast it is. So if you get information, it's at a speed of 350 kilometers, it's this distance, then it's at this speed, at this distance. I mean, the machine will not change very much. So if it's not changing too much, you can have almost everything perfect. So you get your perfect landing. Also, you have uncertainty. But you have different regimes. Probably they are more smart than just having two alternating things. But essentially, that's what I think is, if you're doing this spectrogram analysis, it's really meaningful, and I have not too many practical applications or so, to think of the possibility of dealing offline. So to have recorded it. Now I want to do analysis with this window, this window, this window. And I get some information from long windows. I get other information from short windows and so. And so normally we are concentrating too much, I think, on choosing one window and what is the best window. And I would say there is no best window if you think in these more practical terms, but maybe there is a collection of windows that together, if you reorganize your information, are optimal, are better than any single window can be. Okay, thank you, and we will continue after break.